Okay, so maybe let's start. So welcome to the last lecture. So last time we discussed these Rousseau-Seymour-Welch results and quasi-independence. And thank you for mentioning this recent paper of Tassion. I have looked at this, had no time to read it properly, but it seems that indeed they managed to prove Rousseau-Seymour-Welch without quasi-independence, so they just need some regularity and positive association. Although the paper is formulated in terms of discrete percolation, but they're writing that the same argument holds for fields as well. I will have to check the argument, but probably it is so. Okay, so now the problem with these quasi-independence arguments using discretization is that these results are highly non-optimal, and the problem is that really our standard estimates for quasi-independence of Gaussian vectors, they are very sensitive to a lot of things. So, for example, if you just say sample field at one point and then sample it at 1 million points extremely close to this one, then in some sense, this extra sampling does not give us any essential information. On the other hand, it completely ruins quasi-independent results. So this really suggests that this discretization is not the optimal thing. And so far, it seems that a much better idea is to use a different finite dimensional approximation. So what we have been doing so far was essentially this. So we have some points xi, and then we replace field by collection of its values at these points. And so now instead of our field, which is a Gaussian vector in infinitely dimensional Hilbert space, we have finite dimensional Gaussian vector. But there is a very different idea of finite approximation, which makes much more sense. So we have some Hilbert space H. This is our Cameron Martin Hilbert space. Can we find some other space Hn, which, well, it might be a subspace or might be actually not a subspace, but close to H in C infinity. So in some sense, Hn is close to H in, well, maybe CK or something like this. Simple example. So we write our field F as sum of AI phi I. Then we can consider, so this is an example. Consider Hn to be span of phi I from 1 to n, and then Fn is sum of first few terms. And then we know that Fn is close to F, not only in H norm, but also in CK norm, well, provided that our covariance is nice enough. But so, and now I want to make a couple of important comments. First is that how close Fn to F is not an intrinsic property of the Hilbert space. So this is property how fast our series converges in C, and this is not universal thing. So it might be that if you want a good approximation within given compact, then you can optimize it by choosing a different basis. And this is a funny question from functional analysis, which is very unnatural from functional analysis point of view, but very natural from this one. So what is the optimal rate of convergence? So if I have some functional space made of functions that are, say, CK smooth. Then I fix a compact. And then I want an orthonormal basis in our Hilbert space, such that on this compact, our basis is as localized as possible. So that when we write covariance kernel as sum of phi I of x, phi I of y, that this series converges as fast as possible. To the best of my knowledge, this is an open question. But in theory, we can do something else. So for example, if you go back to this discretization, then if you know values at given points, then, for example, you can take linear interpolation, and now we're approximating F by piecewise linear functions. Or maybe we interpolate by something else. Or maybe instead of interpolation, we can use something else. So, for example, you expand F, I know, in Taylor series or Fourier series and truncate them. So there are a lot of possibilities. So, and this kind of functional approximation usually works much better than special approximation. And
yes. Can I ask a question? I know that there is a Carhoon-Loew decomposition, yes, and it has this optimality property that
yes, but
precisely
it's optimality in a kind of wrong sense. So it's L2 optimality.
Yes. So and here we want like CK.
Uniform. Yes, and here we want the CK optimality. Yeah. So yes, you're absolutely right that it's in the same spirit, but in a different norm. But yes, so this result is exactly in the same spirit. So we have Hilbert space with one norm, and then we want optimality with respect to some other norm. But there we look at L2 optimality, and here we want CK optimality.
Yeah, thank you.
But yeah, they're kind of related things. Okay, and probably first result in this direction was done by Rivera and Vanderbilt. So they proved that in 2D, so Rivera so in R2, if you basically have two, say, let me state in terms of boxes, then you have event A, so this is, say, subdomain omega 1, omega 2, then we have domains AI that are measurable with respect to what's going on in omega I, and then we have this parameter eta, which is supremum of k x minus y, x in omega 1, y in omega 2. So this is supremum of pointwise correlations. Sure. And then, well, we want more. So actually AI, there are events generated by crossings. I don't want to go into details about what it means exactly, but we can consider events like this. Say we split it like this, and we want an event that we have, say, horizontal crossing here, vertical crossing here, and horizontal crossing here. So these type of events are allowed. And then we look at probability that both events happen. Then this thing is bounded. Well, there are some constants, but basically we have eta, and then we have area of, area of omega 1 plus length of d omega, well, I, and then we have product. In particular, if we talk about our previous results, when boxes are of size s and distance between them of order s, then what we have is, and k of x behaves like x to minus alpha, then what we have then eta is of order s to minus alpha, and if boxes are nice, so they're really boxes, but we can look at domains with more complicated boundary, then area is of order s squared, and we have product of areas, so we have s to the 4. So we have a quasi-independence when alpha is more than 4. And later they proved a different version, but under much stronger assumptions on the field, that if events are not only generated by crossings, but in some sense they're generated only by crossings of one color, so they're increasing events, then you can push quasi-independence to alpha being greater than 2. But so far, this is only two-dimensional thing. But later it was generalized to higher dimensions. So it's possible to do these, well, similar results in higher dimensions. And this was done by myself with Muirhead and Rivera. And this was 2 years ago, and now it's in RM. So we want to look at something which is called strong mixing. So have you seen notion of strong mixing before in any context?
I don't remember.
Okay, so Let's start with one-dimensional thing. So it's actually a very classical result. So let's assume that we have a stochastic process. And then we look at the following thing. For simplicity, I will assume that my process is stationary, but actually this notion can be defined for non-stationary as well. So stationary process in R. Then we look at the following mixing coefficient. Alpha S is supremum PAB minus PAPB. So we look at covariance between events, and one event is measurable with respect to whatever happens, say, from minus infinity to 0, and another from S to infinity. So we have gap of size S, and then we have one event on one side of this gap, another event on the other side of this gap. And strong mixing means alpha S goes to 0 as S goes to infinity. So when we look at events that are separated from each other, then they decorrelate. Well, actually, it's not quite true that they decorrelate. We're not talking about correlation. We're talking about covariance. So these are, of course, slightly different things. Because, of course, if you look at events that are extremely rare, they could be very strongly correlated, but this difference is small because just all probabilities are small. And strong mixing was studied a very long time ago. So there is a classical result of Kolmogorov and Razanov from 1960. That if alpha goes to 0, then if you look at this integral, then it converges where rho is spectral density. And now, actually, this is one big problem with strong mixing for our fields. There is no strong mixing for analytic fields independently of how fast correlations decay. So they can decay arbitrarily fast, but analytic fields are never strong mixing. And the reason is very simple. Well, if we have this gap, basically, if you know the entire sigma algebra, so complete knowledge of F on actually any open set gives complete of F on the entire space. Because if our thing is real analytic, then we can just extend our function. So that's it. So if you know everything about analytic function on a small set, then you have it everywhere. The problem is that analytic functions are extremely rigid. So it means that for analytic fields, there is no hope that they will mix. But on the other hand, events that do not decorrelate, they're not events that we care about. And now let me introduce notion of topological events. So we work in a language of stratified sets. So basically you have some box, which is just basically it's a manifold. So one way to think about it, it's manifold with corners. So you basically represent this set with boundaries. So you have like open two-dimensional thing, then you have one-dimensional side, and then you have kind of corners. So we split our set into kind of strata. So we have two-dimensional strata for, in this case, for one-dimensional strata and for zero-dimensional strata. Or we can have more complicated things like we could put one more strata here, then kind of we have two-dimensional strata and something like that. And then we look at topological events. So topological events are events measurable with, so we identify nodal domains up to homotopy which preserves stratification. So what do I mean by this? We look at classes of equivalence of topological pictures for nodal lines. So for example, if you have this picture, then it's, say, homotopic to, I know, this picture, but it's not homotopic to, for example, this picture. So although without stratification they are homotopic, but here this line connects two different sides, and here it connects the same. So our homotopy must respect stratification. So is it clear what kind of events are we considering?
Yep.
Okay, so these are topological events, and then under extremely mild regularity assumptions, and in particular, we do not require our fields to be centered. It means that if we talk about centered fields, instead of level sets, we can look at sets where function is above or below certain deterministic function. But we have the following theorem, that if AI are topological events in stratified sets BI, then we have, and now this is an amazing thing. So far, everything I mentioned was an estimate. So we always estimated things. And now it's the first thing where we have an explicit formula. So covariance between these two events is given by an explicit formula. So we integrate over this product covariance. And by the way, again, we are not assuming that field is stationary. Field can be non-stationary. And then we have two measures. And these two measures, so first of all, they are measures on stratified sets. So basically what I mean is that a measure pi is made out of several pieces. So on two-dimensional strata, it's two-dimensional Lebesgue measure with certain density. On one-dimensional strata, it's one-dimensional measure with certain density and so on. So this measure pi is actually sum of like Hausdorff measures of different dimensions sitting on stratas of corresponding dimension. And so on each stratum, P plus minus are continuous up. Well, they're positive, so that's why we split. And continuous with respect to Lebesgue measure on these stratum. And densities are given by explicit formulas in terms of K and its derivatives. So these formulas are a bit horrible, so I'm not going to write them down, but they're absolutely explicit, and so it's easy to write some estimates. But the beauty of it is that it's not just estimate, it's an explicit formula. And one immediate corollary is that if we look at strong mixing, so we look at, again, the same kind of notion of mixing. So we look at supremum of covariances between events measurable with respect to B1 and B2, but now we look not at all events, but only events in sigma algebra of topological events. So this is topological mixing. So this is bounded by some constant times B1, B2, Kx minus y dx dy. Well, f is stationary now. Which immediately gives generalization of Rivière-Vanderbilt, because if K is bounded by this, then this is bounded by area of B1 times area of B2 times distance between B1, B2 to minus alpha. So this is exactly what we have here. Okay. So we have this estimate. And another corollary is that, well, basically by definition of these measures, P plus and P minus, if AI are increasing, then P minus is 0. and then we have FKG. So it gives us a kind of a, alternative proof of positive association. Okay, so let me just mention a couple of words about the ideas behind. And the idea is actually, part of the idea is something which is very similar to Pitt's proof of positive association. And if you have never seen this trick, it's a very nice and beautiful trick. How can you deal with covariances? So one way to think about it is that we compare what happens with events A and B if they are correlated the way they are correlated, and situation where they are independent. And so the idea is to kind of interpolate between these. And what you do is you look at the following well, let me give a finite dimensional version, which is a beautiful lemma by Peter Bark from 70s. I don't remember when exactly. So let's look at, so we have X, which is a standard n-dimensional Gaussian vector. And then we take X tilde, independent vector with the same distribution. And then we look at these two n-dimensional vector. So this is X and Tx plus square root of 1 minus T squared X tilde. So so first of all, law of these, so both parts of Z, they are standard Gaussians and two-dimensional standard Gaussians. But when T is 0, they are independent, and when T is 1, they are identical. So we kind of interpolate between pair of identical Gaussians and pair of independent Gaussians. And then if you look at this probability, so we take A and B, just two nice sets in Rn. Then you just, so the proof is you write explicitly density, integrate by parts, and then you get integral over product of boundaries. Then you have outward normal vector to the boundary of A, normal vector to the boundary of B. So you get this. And then when you integrate from 0 to 1, what we have is that probability of Z1 in AB minus probability of Z naught in AB is equal to integral from 0 to 1 dB something like this. And now if you look at this, when when T is equal to 1, then Z1 is two identical copies. So Z1 is XX. So first probability is just exactly the probability that X is in A intersect B, and Z0 is X tilde, so we have probability that X is in A times X, sorry. Is in B. So that's exactly our kind of, so when we look at events that our Gaussian vector is in certain set, then we have an explicit formula for covariance of such events. And now our X is our kind of Gaussian vector, and our events are the kind of event is that nodal sets of our field is in certain topological class. And now we have to figure out what is the boundary of a topological event. And then if you think about it for a while, you figure out that most of the boundary is made of the following things. So if you have a critical point at zero level, then nodal lines cross. And if you function like this is on the boundary of a topological event, because if you perturb it a little bit, it will become either this or this. So you change topology when you perturb around this zero level critical point. And another type of boundary is when you have picture like this. Then again, it might, under small perturbation, it might become something like this, or something like that. But now, this means that if we restrict our field to this boundary, then this restriction has a critical point. And this is why we have to work with stratified sets, because we care not only about critical points of F, but also about critical points of F restricted to strata of different dimensions. And then if you kind of look at what are these scalar products, now kind of our space is space of functions, and these products, they become something like 2-point correlations between events that you have critical points at different places. And so these are kind of joint densities of critical points of different stratas, but when we talk about critical points, these are local observables. So these joint densities can be written in terms of Katz-Rice formulas. Katz-Rice formulas like these are horrible but explicit. And this is how you get these explicit formulas for measures pi. And pi plus and pi minus, they depend on whether positive perturbation, when you perturb positively, do you enter the event or do you exit the event? So that's the idea. Okay. Any questions so far? Okay, now let me return back to the question about number of nodal domains. So as we discussed, this is an interesting observable, and when you have an observable, usually you want to do 3 parts. Okay, so now we're back to number of nodal domains. So essentially, we want three things. First, kind of expectation, and from expectation you, well, kind of a scaling limit of expectation, we also get law of large numbers. This is exactly what we got before, that if you take number of nodal domains in a large disk, rescale by area, it converges to the limit. So this is like law of large numbers. Second step, you get variance, and third step, you get central limit theorem if you're lucky, if not some other limit theorem. It does, well, it kind of converges to whatever it converges to. It doesn't have to be normal. There are other situations where limits are something else. So this part is done. Now we want, and so to prove central limit theorem, quite often, well, you don't really need to know variance, but you need some control over variance. So now what can we say about variance? And there was a progress in last kind of half a year. There are two complementary results. So one result is a theorem by, again, Nazarov and Sodin. It appeared as a preprint this year, but they were giving talks about it for last like 1.5 years. So what they did is the following thing. So we have F stationary field, Gaussian field, and then we assume that F is slightly better than C3, almost surely. And then they have very weak assumption on decay of correlations. So this is kind of a new thing in this business. So as you have seen in all the results so far, we required this alpha to be like at least 1, at least 2, maybe at least 4, depending on what we want. Here, just any polynomial decay will do. Then there is some positive constant sigma such that variance of number of nodal domains in disk of radius r of this field asymptotically greater than radius to sigma. So now what we have, we know that expectation is of order r squared. Then it's not quite hard to show that variance is is bounded by r to the 4, but it trivial estimate is that lower bound is constant. So they proved that under extremely mild assumptions, there is a non-trivial lower bound. And then, of course, conjecture that well, we are not certain what are exactly kind of the right assumptions for this conjecture, but for generic field, variance is of order r squared. And this is consistent with Bhagavan and Schmidt conjecture. Okay, so this is one result. And the second result is actually kind of a culmination of series of 3 papers by Michael Macaulay, Stephen Muirhead, and myself. So we have so unfortunately, I have to formulate a few things before we get to the variance. So these are kind of 18, 19, and 20. So we know that if we look at number of nodal sets, then there is a scaling limit. But the same works with not levels, 0 level sets, but you take any level. And this also works with both excursion sets, so sets where field is above or say below a certain level, and where it's exactly the level. So we use these notations. So number of excursion sets of inside disk of radius r at level L, if we normalize by area, then this converges to certain constant, which we call CES of level. And similarly, if you work not with excursion sets where function is above level, but with level sets, you get the same thing. But now, okay, these are not numbers, they're functionals, they depend on the level, and also actually they depend on, of course, law of our field. And by the way, they depend on this law continuously. So this is a result of Per Kulberry and Igor Wigman. They proved that these functionals are continuous functionals with respect to spectral measures. So they're continuous with respect to weak topology on space of spectral measures. So what we have done is that under some mild conditions on regularity of fields, CES and CLS can be written in terms of densities of critical points. And this allows us to prove that CES and CLS are continuously differentiable functions of L. So when you vary L, kind of number of excursion sets per unit volume changes in a smooth way. And the main idea is kind of Morse theory type of thing. So do you know anything about Morse theory?
No.
Okay, so it's in some sense, it's, well, there are some very difficult technical things, but in some sense, it's a very simple thing. Let me draw kind of one-dimensional picture, but clearly 2D picture is similar, but it's just harder to draw. So let's assume that we have some nice function, so, say maybe bounded. My function is bounded, and so first of all, for a generic function, all critical points are at different levels. And now let's fix some level A and fix some other level B. And now let's look at components where f is above level A. So for level A, it's these intervals, and for level B, it's this interval. And then the following thing holds. So now let's fix a level, and let's look at level A, and let's start changing it. So then these intervals will be moving a little bit, right? But level sets, so these sets, they are homotopic to each other. But then what will happen when we pass through a critical point? Well, when you pass through a critical point, it might disappear. And we know exactly what will happen. So when you pass through local maximum, a level one level set will disappear, and when you pass through, so imagine that, yeah, kind of, we have picture like this. When you pass through minimum, a level will appear. So if you want to compare number of components for level A and level B, what you have to count is how many local maxima are between them and how many local minima. So difference between these two numbers is number of local maxima minus number of local minima. So it's kind of very simple, right? And then if you want to know number of these components at given level, then you can go all the way to infinity. When B becomes kind of infinite, then there are no components left. So it means that number of these components is number of local maxima above this level minus number of local minima. And that's it. It's very simple idea. And when we deal with two-dimensional pictures, say we look at the level. Here we have, say, two disks. We change now, it's kind of still two disks. And when we go through this point where we have a saddle, then kind of so if you look at levels, kind of these sets where function is below it and above, then at this moment, our picture will become this, and then it will become like that. So this is how number of number of excursion sets could change. So when you change level, if you do not cross a critical level, topology does not change. If you cross kind of local minimum, you add component. When you cross maximum, you kill component. But when you cross a saddle, different things could happen. So for example, if you locally, picture looks like this. And when you raise level, it now maybe look like that. But maybe they're still connected. So maybe your picture was, so kind of a cartoon of what's going on was like this. So you had annulus, then it become kind of pinched annulus, and then it became kind of horseshoe. But number of components have not changed. Or it might change, so it might be that you had this domain, and then when you go through critical level, it's this, and then you have two domains. So local minima and maxima, they are predictable, but saddles, they are of two types. They are of type 1 and type 2. And bad thing is that obviously when you look locally at the saddle, you don't know whether it's type 1 or type 2. And you should expect it because critical points, they are local observables. If you were able to do this locally, then of course number of nodal domains would be a local observable, but it is not. That's the difficulty, that it's not local, non-local observable. But still kind of with this representation, it's much easier to work, and this allows us to do most of the work in terms of kind of you change level and you see what's going on when you cross a critical point. And this is almost local analysis. And this is what allows us to prove that these densities are continuously differentiable. Okay? And now we can state the following results. So if C prime ES at level L is not 0, then variance of number of excursion sets is of order R squared. And if C prime of level sets L is non-zero, then variance of number of level sets so when we compare to result of Nazarov and Sodin, on one hand, our result is stronger because we can deal with all level sets, and also instead of some positive power, we have R squared, which is believed to be the correct order. On the other hand, we have this condition that derivative of this functional is non-zero. And this is a condition which is very hard to verify. And what is even harder is that this is especially true for level sets. You see, field is symmetric. So if you multiply it by -1, then it has the same law. So symmetry implies that number of level sets for L and number of level sets for -L is the same. Which of course implies that exactly for in the most interesting case of level sets, of nodal sets, this derivative is 0. And so our argument completely breaks down. So Nazarov and Sodin give weak estimate at 0, but we cannot get anything at 0 at all, at least for level sets. For excursion sets, we can. And so for excursion sets, it quite often works at 0. So in this sense, these two results, they are really complementary to each other. And now let me mention that one of our assumptions there are some natural assumptions that fields is smooth, derivatives are non-degenerate, and so on. But one of assumptions is this. Rho, which is spectral measure, has density near the origin. And this density is uniformly away from zero in a neighborhood of the origin. So this is, so for example, for Bargmann-Fock field, this is true because it has very nice spectral density, which is just Gaussian density. So this is not true for random plane wave. So our argument for random plane wave completely breaks down. Because not only a spectral measure has no density, to some extent we can deal with fields so that there is no density, but what we really want, we want spectral mass near zero to be bounded away from zero. And here it's just not true. For random plane waves, spectral measure sits on the unit circle, so there is absolutely no spectral mass near the zero. So Nazarov and Sodin give some lower bound near, for random plane wave, but we don't. But then we have some other argument which works exactly for random plane wave. For random plane wave, if L is not zero, and so unfortunately we have to exclude zero level, even for excursion sets. Then variance of NES is asymptotically R cubed and very. So unfortunately, this does not work for zero level at all. Even for excursion sets, for which we know that derivative of this thing at zero is not zero, but zero level doesn't work anyway. And what we have is that variance is of order 3, and we believe this to be sharp. So we also believe that for random plane wave, at zero, variance is quadratic, so there is some cancellation. But our methods cannot give this. But there is one very interesting consequence of this. So there is a stronger, even stronger form of Bhagavan-Schmidt conjecture. So Bhagavan-Schmidt conjecture tells us that nodal lines, they look like critical percolation. But then we believe that non-zero critical lines, they believe like of critical percolation. And for example, all these results that I mentioned before about phase transition, they build around these ideas. So this is what happens, for example, for Bargmann-Fock. So here we take level which is just below 0. And then on this picture, black is the largest gray cluster. But when you raise level to 0 level, then you have this. And when you raise it a little bit above, then immediately the largest gray cluster is kind of almost everything. But changes are absolutely minimal, but changes in connectivity are huge. So this is kind of a typical phase transition. So pictures look almost the same, but connectivity is very different. So there is really strong reason to believe that, well, at least for Bargmann-Fock, if you look at level which is not 0, and you look at excursion sets with level above or below 0, then what you will get is either subcritical percolation or supercritical percolation. So either you get a lot of small domains, or you get one infinite domain and a lot of small domains. For percolation, variance of number of clusters is quadratic independently of P. So it doesn't matter whether it's critical percolation or subcritical or supercritical percolation. Variance is of order R squared. On the other hand, this variance doesn't have to survive passing to the scaling limit. So kind of this is some indication that it might be that at least off-critical version of Bogomolny-Schmidt for random plane wave is wrong. But, well, kind of it's an indication, but not a proof. And also, we believe that there is some cancellation at 0, and at 0, variance is quadratic. And so far, we believe, and hopefully will be able to prove this soon, that for generic fields, variance is really of order R squared, and for random plane wave, variance is of order R cubed. So that our estimates are sharp. But unfortunately, our estimates don't work for nodal level lines. So in this sense, kind of really Nazarov-Sodin theorem and our theorem, they really complement each other. Any questions so far? Okay, then let me just, so we have about 20 minutes. So let me just say a few words about what are the ideas behind these two theorems, because they not only get complementary results, they use very, very different ideas. So Nazarov and Sodin, they used, so their idea was to kind of justify arguments of Bogomolny and Schmidt. So in this sense, their proof in spirit is much closer to original argument of Bogomolny and Schmidt. And so in some sense, the idea is still the same, that when you perturb a function, then nodal lines perturb only if you have critical points with small value. So only if you have small critical values, then you can change topology. So if you fix a function and look at its small perturbations, then these perturbations are controlled by low-lying critical points. And then first step of their argument is to carefully choose a level such that there are many critical points in BR with level below. So basically, we look at xi such that gradient in B, gradient is 0. Well, from Katz's number of these points, well, of all critical points is of order r squared. And then we look such that f is below a certain level. Then number of these critical points, at least expected number, is like epsilon r squared. And then it's possible to choose epsilon so that number of critical points such that f less than epsilon is large, so it's more than some power of r. But they all are well separated. So distance is more than r to some other power. So there are many points, but they are for many low-lying critical points, but they are far away from each other. And second, you perturb your field. So you look at field, which is your original field plus small perturbation. G is an independent copy. Then, of course, field F tilde has the same law as F. But if this, say, let's look at nodal line for F. And here we have a low-line saddle. Then if G is positive at the low critical point, then, and here we have F is, say, negative. And here F is positive. Then for F tilde, we'll have this thing. Okay? And if G is negative, then in opposite situation, we can change topology. So what happens is that if you look at these low critical points, around each critical point, we have this type of picture. Nodal lines almost cross. And outside, they're connected somehow. And so when you add G, you make some perturbations here. And these perturbations, they are positive or negative with probability 1/2 because of symmetry of G. And they are almost independent because critical points are far apart from each other. And they're well separated, so they're far apart, and our covariance kernel is decaying. So when we look at points that are far away, they're almost independent. So we have this like almost independent percolation on this funny collection of loops. And this is almost Bernoulli percolation. And for Bernoulli, when you have bench of Bernoulli random variables, there is something which is called anti-concentration. So Bernoulli random variables cannot really concentrate too strongly around their mean. And this is true for every functional. And from this, you get an estimate on the variance. So that's kind of roughly how what are the ideas behind Nazarov and Sodin proof. And our ideas are completely different. So this is a very, there is a very beautiful lemma due to Chatterjee, but methods like this, they appeared actually many times throughout the history of probability, but I think Chatterjee is the first to kind of distill it and give a precise formulation. So I'm not going to write it precisely, but the idea is this. Imagine that you have two random variables on the same probability space. And total variation distance between these random variables is small. But there is certain reasonably large probability that these two random variables are not very small. Then they must have large variance. So that's the idea. So we have sequence of random variables, xn and yn, random variables on the same probability space, and we have sequence of parameters that are positive. And then we assume that xn and yn are not very close to each other. So there are some constants C1 and C2 such that probability that xn minus yn is more than C1 un is at least C2. So we have uniform control. So xn and yn are, well, cannot be kind of too close to each other on scale un. And then we also assume that total variation distance between xn and yn, that this goes to 0 as n goes to infinity. Then xn has fluctuations of order at least un. In particular, variance of xn is of order un squared. So this is one way how to get a lower bound on variance, because usually actually getting upper bound on variance is a reasonably simple task, but proving lower bounds on variance is usually hard. So this is one way how you can get a lower bound on variance. And then we apply these to the following sequence. So we have XR, which is, say, number of excursion sets in ball of radius R at level L. And then we compare it to YR, which is number of excursion sets in the same ball, but at some other level, which we will choose carefully. Then, what can we say about these? So, how different they are? Well, and this is where we use, so remember we have this condition that CES prime of L is not zero. So it means that when you change level, density of level sets changes by kind of derivative times increment of the level. So it means that this difference is of order derivative of CL, well, it's just some constant. So density changes by AR times derivative. And since this is density, numbers change by like R squared AR. And this is why we need this. And then to get total variation distance between XR and YR, well, they are functionals of our field, but let's think that, well, YR is, well, it can be reformulated that it's also number of excursion sets at level L, but function which is F minus AR. So now we have the same function, but of two different fields, F and F minus AR. So when we have one function of two fields and we want total variation, it's obviously bounded by total variation distance between fields themselves. But this can be done by Cameron-Martin theorem. So you approximate identity in the unit disk, in disk of radius R by functions from Cameron-Martin space. And in order to do this, we need, so this is where condition about spectral density at zero appears, because if you want function 1 to be in, constant 1 to be in your Cameron-Martin space, then spectral measure should have delta function at the origin. But if it has some density around origin, you still can approximate identity. And there is a theorem which tells you exactly what happens about total variation when you change your field by an element of Cameron-Martin space. And basically, this goes to zero if AR is much smaller than 1 over R. And together, this means that our level, so fluctuations, they are of order R. So we have to take AR to be 1 over R, then our random variables differ on scale R, so fluctuations of order R, and variance is of order r squared. And for random plane wave, method is somewhat similar, but we cannot approximate identity by a function from Cameron-Martin space, because Cameron-Martin space is made out of eigenfunctions of Laplacian, and one is not an eigenfunction of Laplacian, nowhere close. But remember that for random plane wave, we have this power series. And there is an important fact about Bessel functions. So if you fix in a ball of radius r, Jn is exponentially small, if n is more than, say, 2r. So Bessel functions, if you now think that n, you fix r and send n to infinity, basically all functions with numbers that are more than r, they're extremely small, which means that f is equal to sum of first, like say 2r terms plus essentially small thing, which means that everything is totally controlled by first approximately r coefficients. And then you can estimate distance between xr and yr. So instead of comparing field and field minus constant, we compare field and rescaled field. So we look at f and l plus ar, f. So level L plus AR of the field is the same as level L for rescaled field. But this is approximately, since our field is completely determined by R independent Gaussians, by these coefficients. So this is basically total variation distance between standard Gaussian of size r and standard Gaussian multiplied by so this is kind of identity matrix of size r. And now this is a standard result, so it's clearly kind of, it was computed long time ago, what is total variation distance between two Gaussians. And it turns out that this is like r AR squared. So it means that we can take AR can be taken like O small of 1 over root of R. And then fluctuations are R squared over root of R. So this is R to 3/2. And so variance is at least R cubed. So this is the main idea and behind it. And as you can see, this is where we really need this fast convergence of series for Bessel function. And I think this is exactly everything I wanted to say, and this is exactly where I ran out of time. So this is the end of this course. I would like to thank you for staying with me for these lectures. Do you have any questions? Okay, then if not, so again, I will upload the lectures and lecture notes to the course to the course page, and you can consult with them, or you can ask me any questions. So you know my email. You're very welcome to contact me. Thank you.
Thank you for the course.
Thank you very much. It was very interesting.
Thank you.
Thank you.
Goodbye.
Bye.